Okay, so let's do some practice word problems with acceleration. Now please remember, saying I didn't know what equation to use is not a valid reason for skipping your homework. All of these equations can be used at any time. Which one you choose to use is going to be based on what you're given as the knowns in that particular problem. So let's start with this first problem. We will list out our knowns. We are told that this car can finish a 180-meter drag race, so we know our delta x is going to be 180 meters, and it does it in 3 seconds, so our time is going to be 3 seconds. What minimum constant acceleration is necessary? So we're asked what the acceleration is, so we'll make acceleration a question mark. And then we do have to read a little bit closely to see that because this is a race, we know that the initial velocity is going to be 0 meters per second. So we now need to think to ourselves, what algebraic equation combines delta x, delta t, a, and vi? So you guys can refer to the notes a little bit higher up where we listed out all 4 kinematic equations. And hopefully you will see that delta x equals vi delta t plus 1/2 a delta t squared has all 4 of these knowns in it. So we can fill in everything we know. Since that initial velocity is 0, that whole thing goes away. And we're left with 1/2 a times 3 seconds squared. And from here, it's all just algebra. So we square the 3 seconds, we divide it by a half, we do 180 divided by whatever that is. But when you finish the algebra, you find that your acceleration is going to be 40 meters per second squared. And that's the answer. So let's do another practice problem. A car on a wet road can achieve an acceleration of only -1 meters per second squared without sliding. Find the required stopping distance for a speed of 5 meters per second. So we write out our knowns. We know that we've got an acceleration of -1 meters per second squared. We want to find the required stopping distance, so we're trying to figure out what delta x is, and since we are stopped at the end, we know our final velocity is going to be 0 meters per second. And then we are told that we have an initial velocity of 5 meters per second. So this one's pretty easy because we don't know the time, and not knowing the time is a clear indication to us that we need to use the equation that does not have time in it. Vf squared equals vi squared plus 2a delta x. So our final velocity was 0, so this becomes 0 equals 5 meters per second squared plus 2 times -1 meters per second squared times delta x. And yet again, it's all just algebra from here on out. So we algebraically solve for that delta x, and you should get a delta x of 12.5 meters. Let's do another example problem. An aircraft has a landing speed of 20 meters per second. Let's see, so when we make our knowns, we've got a landing speed of 20 meters per second. The landing area is 200 meters long. What is the minimum constant acceleration required for a safe landing? So we're trying to land this plane. So they're trying to say to us that that 20 meters per second is our initial velocity. We want to land this plane, so we would hope that at the end we would be stopped. So our final velocity is 0 meters per second. The landing area is 200 meters long, and we want to know what will our acceleration be. It looks like we have the same knowns that we did above. Yep, we know VI, VF, delta x, and a. So we're going to use VF squared equals VI squared plus 2a delta x. So since our final velocity was 0, we get 0 equals 20 meters per second squared plus 2 times our mysterious acceleration times 200 meters. And boom, it's just algebra. We just don't know what that acceleration is, and if you solve the rest of this problem, you should get an acceleration of -1 meters per second squared. That negative is very important because we know that from the last lecture, the combination of the direction of velocity and direction of acceleration tells us whether we are speeding up or slowing down. And since our velocity is a positive number, if we want to slow down, we know our acceleration has to be a negative number because those opposite signs tell us that we slow down. So that's great because that tells us that I think we did this right. Let's do one more, or actually two more. A plane starts at rest at one end of a runway, undergoes a constant acceleration of 4.8 meters per second squared for 15 seconds before takeoff. What is its speed at takeoff? So again, the first thing we will do is we will make a table of knowns. The plane starts at rest, so our initial velocity is 0 meters per second. It undergoes a constant acceleration of 4.8 meters per second squared, and it does it for 15 seconds, so our time is 15 seconds. We want to know what is our speed at takeoff. We're going to call that the final velocity. So VIA, delta T, and VF, I believe that all four of those things are present in VF equals A delta T plus V high. So we want to know what this final velocity is. We know that the acceleration is 4.8 meters per second squared multiplied by that 15 seconds plus 0 meters per second as our initial velocity. So if we take 4.8, multiply it by 15, we should get a final velocity of 72 meters per second. Let's do the last part. Using the information from question 5, how long is the runway? So now instead of saying question mark, we could say, okay, VF is now 72 meters per second, and all of these knowns come with me down here. We know a lot of information, so we could look at this and say, well, delta x equals VI delta t plus 1/2 A delta t squared. I could use this to figure out the length of the runway since I know VI delta t, the acceleration, and I'm looking for that delta x. So if we use this to solve, we know that the initial velocity is 0, so all of that goes away. We're left with 1/2 times 4.8 meters per second squared times 15 seconds squared. And we end up getting a displacement of 540 meters. But this is really just one way that we could have solved the problem. We could have solved the problem using a different equation. We also have VF squared equals VI squared plus 2A delta x. We know that that final velocity is going to be 72 meters per second. That initial velocity is 0, so that goes away. We got 2 times 4.8 meters per second squared times delta x. I could solve for delta x this way. And we get a delta x of 540 meters, which is exactly the same delta x that we got by solving this problem using a completely different equation. So that's what I'm talking about when I say that these equations, really you can use any of them to solve any problem. They all will get you there eventually. It's just that some of them are a little bit more obvious than others. The wonderful thing is also it means that we have multiple ways to solve problems in physics. So you could solve the problem a different way than your friend solves the problem, and you both can arrive at the same answer. It just means that you should do whatever you feel comfortable with. So good luck solving those acceleration problems.